All right, shall we get started? So first of all, some of you were asking me about the dates of the exams, the midterm and the final. So I finally did schedule the midterm I posted on Piazza. I think it will be October 21st and 23rd, because you should split it into two classes and virtually have just 1 hour each. It would be too stressful if you had to do everything during 1 hour, so I'll give you 2 hours. And the final, I think that's already been scheduled actually. I think it's going to be December 12th, 6 to 8 p.m., but I yet have to double check on that. Then I've also posted online. So the dates, yeah, I'm working on it. Do you have any questions regarding to that? I don't know what room it will be in yet, the finals. The midterm is going to be just here in the class. That's I think how it usually is. Okay. Yeah.
What about the percent of our grade each one is worth?
Oh, there was a slide. Oh, and somebody wanted the slides, so you don't have to go to YouTube and then scroll through it. I understand. So I posted the slides on Canvas. You should be able to find them, just like the homework and all that stuff. And one of these slides on the introductory thing was like this percentage breakdown, like how much is what. I don't really remember. I can put it on the website too if you really want, but. If you want 100%, you probably want 100% everywhere. Now it's more or less like equal. Something slightly more, something slightly less. Okay. Any other questions? So today we will do the elementary group theory, because group theory is intimately related to matrix multiplication. But first of all, I think I owe you explanation of the transpose versus inverse for orthonormal matrices, right? That's what I sort of did not finish the last time. So we were talking, actually, let's recapitulate that real quick. So we were talking about a transpose of a product. ABT is BTAT. Oh, we wanted to do the light stuff. Work. Good focus. So that's for the transpose. And for the inverse, we had the same thing almost, right? That the inverse is B inverse, A inverse. And in fact, for certain special matrices, transpose is the same thing as inverse. So this is the case for orthonormal matrices. That's what we discussed during the first or second lecture. So they are denoted as ON, like capital O, like orthonormal. Don't confuse it with like the asymptotic complexity. This is like the set of orthonormal. So this is like a subset of the n by n matrices. So how were orthonormal matrices defined? Let's recapitulate that. So if I look at the columns of an orthonormal matrix, then what is true? Do you remember? When was the matrix called orthonormal? So there was some condition involving the dot products of the columns. Yeah.
Were they all normal to each other? All the column vectors?
Exactly, yeah. That's right. If I take dot product of two different columns, I have to get 0. And if I take dot product of a column with itself, or the length, the squared norm of the column, I have to get 1. You could also talk about orthogonal matrices, which would have just the first property, and they would not have to have a length 1 columns. But it's just like a very, very subtle distinction. Normally, you can just talk about orthonormal matrices. So I can write it succinctly like this. AI, AJ, do you know this notation, delta IJ, the Kronecker delta? The delta IJ simply means that it's 0 if I is different from j, and it's 1 if I is equal to j. So this is just a fancy way of writing that if I and j is the same, then it has to be 1. And if I and j are different numbers, different indices, then it's 0. So if they are different, 0 means they are orthogonal. And the fact that AI transpose AI, that's the squared norm, the length, right? And that means that the length is unit. That gives it orthonormality. So this is how orthonormal matrices were defined. So if this is true for all columns, for all ij, so I should also write here like for each, I guess like this, right? I, j, like this. So this is true for all ij, then we talk about an orthonormal matrix, right? And what is cool about orthonormal matrices, why I'm even saying that here, is that I have a C which is orthonormal, then the inverse of C is exactly the transposition. So computing inverse of an orthonormal matrix is super simple. All you need to do is just transpose. Why is that? It's actually fairly trivial. So let's say this is my matrix C, and I look at the columns of matrix C. It has to be square. You could be talking about orthogonality for also non-square matrices, but this ON refers to just square matrices. Let's not complicate things right now. So what I'm trying to show is that the C transpose, so how does C transpose look like? That's what we were talking about on Monday. So what I need to do to get C transpose, this is my C, and here I'm trying to write C transpose. So what do you think I'm going to write here? Exactly, the columns become rows. So this is going to be C1t and so on up to Cnt, right? And this is going to give me some product. And what is going to be here? So the first, I did it actually wrong. I should have done it the other way around. Sorry about that. I should have picked the rows from here. This is really just the notation, right? And the columns from there. So forget about this. I mean, they are still the same matrices, right? It's just how am I denoting the rows versus columns. So this is still C, this is still CT. And what the product is, now I have what I wanted. Now the first element of the product is going to be C1 transpose. Transpose is R. I'm doing so many mistakes today. No transpose is here. Transpose is here. So here I'm going to have, now it's all correct. Now I'm going to have 1 because here I have C1t, C1, right? And if the matrix C was orthonormal, that means it's the same index, delta 1, 1 is 1, so this is 1, right? And all the other guys here would be C1t, like here I would have C1t, C2, but that's 0. Right? Here I would have C1t, C2, C3, and so on. So the rest are just zeros. Do you see it there? That I'm doing the matrix multiplications. I'm taking rows from the left matrix and columns from the right matrix. Right? We have been through that. So what I get here is identity matrix. And that means that CT indeed is the inverse, right? Because that's what the inverse must satisfy. If I have a matrix such that multiplied with the matrix gives me the identity, then this is the inverse. So this means the CT is the inverse. And it really follows directly from the orthogonality. If we had only orthogonality and not orthonormality, we would just get some diagonal matrix and the lengths would be on the diagonal. I think the camera needs to warm up or something before it starts working nicely. Okay. So for orthonormal, so we had some examples of orthonormal matrices, right? Less rotations, permutations. And the one thing I wanted to explain you is that there are actually 2 types of orthonormal matrices. Maybe I'll do it on another paper. So we are talking about orthonormal orthonormal matrices can be either a rotation or reflection. So this is important, for example, when we are dealing with rigid bodies, because rigid bodies can rotate, but cannot reflect. So what I mean by reflection, for example of reflection would be in 2D would be this matrix. So what this matrix does, the y coordinate is unchanged, right? And the x coordinate flips, right? So if I have something like this, then after the transformation, this flips like this, right? It's like a mirror image. Like if the y-axis was a mirror and this is mirrored around the y-axis. So this is this matrix. You can immediately see that, of course, it is orthonormal, right? The length of the first column is 1, the length of the second column is 1, and they are orthogonal. If you do the dot product, you get 0, right? But it's not a rotation, it's a reflection. So how do we tell if an orthonormal matrix is a rotation or if it is a reflection? We can tell that using determinant. We will be talking about determinant more later on, but I can just tell you quickly what it is for 2x2 matrices. So determinant is a function for 2x2 matrices that assigns it a real number. And it's simply for a matrix A, B, C, D. The number is simply AD minus BC. That's the determinant of a 2x2 matrix. So some number that characterizes something about it, tells us something about the matrix. There's lots of important properties, and we will talk more about determinants on a later lecture. It gets a little more complicated for higher dimensional matrices. For 3x3, it's still relatively simple, but for 4x4, these formulas are getting to be a little bit more funny. And one property that's true for orthonormal matrix, so if C is orthonormal, then the determinant of C is either +1 or -1. And if it's +1, then it means that it's rotation. And if it's -1, it means reflection. So the sign of the determinant, it always has to be 1, but it can be plus or -1. And the sign tells us whether the matrix is a rotation or reflection. So for example, I was in 2D, our rotation matrices look like this, right? That's a general rotation matrix in 2D, parameterized by the angle, right? So if I compute the determinant, what do I get? I get cosine square of theta plus sine square of theta, right? There was one minus, and there is minus here, so the minuses cancel, and this is 1. So this indeed is a rotation. On the other hand, this is an example of reflection. If I compute the determinant, I get -1, right? Just use this formula. So here A is -1 and D is 1 and BC are zeros. So AD minus BC is -1. So this is, I just wanted to explain the relationship between rotations and orthonormal matrices. So rotations are orthonormal matrices, but not all orthonormal matrices are rotations, because some of them are reflections. An interesting thing is if you compose two reflections, you get back a rotation. But we will do more of these details later when we talk properly about the determinant. You have a question?
Are reflections like equal to rotations in three-dimensional space of 2D objects in homogeneous coordinate systems? Can you say that? Like this reflection is the rotation around three-dimensional y?
That's a very good observation. So you are thinking that if we lift it to the homogeneous space, if you could model it with a rotation.
If you add like a row of zeros, one in the corner, then another column of zeros on the right, and then you multiply it by rotation around y, would be the same as reflection in 2D across y.
So you mean like doing the projective thing? I don't know off the top of my head. I would have to think about it. It's an interesting idea. Yeah, it looks like that you could just lift it and rotate it, right?
Yeah.
So yeah, I think you could say that. You could create a 2D reflection by lifting it to 3D, doing a 3D rotation, and then doing a projection. Somewhere there would have to be like hidden the matrix with like negative determinant. Yeah, but that's like an advanced question. It probably would be good to like return to that later on. Any other questions? But thank you. Okay, cool. So I think it's time to look into the group stuff. Group theory. So I guess I should first start with some motivation. So the group theory is essentially an abstraction, similar abstraction as like vector linear spaces we started with, where also an abstraction of some mathematical object we can do something to. The abstractions are useful if you like know programming. You know that sometimes there are like abstract classes which like define an interface, some sort of template, you know, like with code. And then you provide specific implementations, right? And then they all fit this one abstract model. So the group theory is also like this. It defines this concept of a group, which can be really anything, or no, it cannot be anything, but there are very many examples of objects that behaves as groups. And matrices actually will be one of them. That's why it fits in here. So the group theory will immediately have consequences to things dealing with inverse matrices, which we will get to in a little bit. So what is a group? So it's abstract algebra, so it's sort of similar sort of deal as with vector spaces. So you start with some set, right? So set can be either finite, it looks like finite number of elements, or infinite, but there is like infinitely many things, and even the infinities have different sizes, right? You probably know that the set of integers is like a different type of infinity than the set of real numbers. That one is actually bigger than the other. But this is sort of funny set theory thing. But sets by themselves would not be as interesting unless we give them some operation, something we can actually do with the elements of the set, right? And what we do with it in the groups is this operation like multiplication, group multiplication, or just group operation, which has to satisfy these three properties. So fortunately here we have just three properties and not 10, like in the case of linear spaces. So let's look at them. All of them are sort of very meaningful and very important. So the first one says that if I pick two elements from my group and I do the group operation, then I get another element which is in the group, right? I don't go somewhere outside. That would be weird. So if I take any A and B from my group G, then the result of my operation, of my group multiplication, must be in the group. So I like to write like the type of things, being a programmer. So you can also say that the multiplication is a mapping from G times G to G, right? That's essentially what this closure says. This operation takes two things from G and returns another thing from G. So it's essentially giving you like the type of the function, if you like to think programming. The second property, we have seen it already. That's like very fundamental property in abstract algebra, associativity. So again, it doesn't matter if we first multiply B with C and then with A, or if we first do A dot B and then multiply with C. Oh, by the way, don't confuse this dot with dot product. It looks, yeah, that's why I didn't like this dot product notation for dot product to begin with. This has nothing to do with dot product. This is the group operation. And that has to be true for any three ABCs in the group. So standard associativity, you have seen that quite a lot, I think. And the last and maybe most distinct property of groups is that there is, first of all, there is an identity element, which I denote here as lowercase e. And this identity element has the property that if I multiply with any element from the right, I get back my element A. So for any A in group, A dot A multiply with E, or A dot E, is back A. So it does nothing, essentially. It's like multiplying with 1. Except that now we are abstract, right? Can be numbers. I will give you examples on the next slide. Can be numbers, can be matrices, can be linear transformations, can be really whatever, almost. And the identity element ties to inverse. So that's the other thing we require. From every element in the group, there must be an inverse element, such that if I do A times the inverse, I get back my identity. And the E is the identity element. So one of these guys is special, one of these guys is E. And it's special because it does nothing in this operation. It just returns, it's just identity. By the way, I don't have any commutativity here. So I must be careful when doing, because in general, A dot B may not be the same as B dot A. Those might easily be two different things. Now there are special types of groups which do have commutativity. Those are called abelian groups. But in general, we are dealing with non-commutative groups, right? Like when we are dealing with matrix multiplication, you know, the matrix multiplication in general is not commutative. But it's fine because it still will form a group, as I will explain in a little bit. But remember, there is no commutativity in general. No, I mean, write it here. So let's look, it's always good to look at some specific examples. Organized. So here are some examples of groups. So the first example is actually the case where you do have commutativity. So the first example is I take all integers, so -1, 2, 1, 2, 3, 4, also -2, and so on. All integers and the operation of addition, so adding two integers. So the closure is obvious, right? If I add two integers, I get an integer. Associativity also follows from associativity of addition. That's trivial. What about the identity element? What's going to be the identity element there? 0, exactly. I can add 0 to, oh yeah, I should have probably put it there. You need to watch for me. I'm doing lots of mistakes today. And what is the inverse in this group? Yeah. Just negating the number, right? If I have number 3, then I take -3, and adding them gives me my 0. So that's an example of perfectly valid example of group. In this special case, it's an abelian group, so I actually have commutativity. Another very classical example is the set of all real numbers. So I can imagine like a real line, except for 0. I have to take the 0 out because 0 I cannot really invert. And the group operation on real numbers can be just regular multiplication. So then what is my identity element there? Simple. Not a trick question, it's just 1, yeah, of course. Because 1 multiplied by anything gives me that anything back, right? That's nothing special. And inverse is just inverse, right? It's just 1 over a. That's why I had to take the 0 away, because the 0 wouldn't really work. I cannot really divide by 0. Or I could, but I would have to define it somehow, and there is no easy way to define it. So yeah, this is the second one is another very elementary example of a group. The third one is a little more exotic. If you take all binary n-bit numbers, so for example 3-bit numbers like this, or this, or this, and you take the XOR exclusive OR operation, you know XOR? No? Like AND, OR, XOR, huh? Okay. So maybe I can just write it quickly here. This is how XOR works, right? So this is A and B, then A XOR B is 0, 1, 1, and 0. So this means XORing all these n-bit numbers together. And interestingly enough, this is also a group. So this is an example of a finite group, right? Because there is only a finite number of numbers. So what is the, this is very slightly tricky question. What is the identity element there? The associativity is not super simple to, I mean, it's not difficult, but it takes some thinking. So the closure is obvious, right? But what do you think is the identity element there on XOR? Something that if I XOR something with, it does not change it, right? Huh?
It's a 0 or 1.
Yeah, all zeros. All I need to take is all, because 0, if I XOR 0 with 0, I get 0. If I XOR 1 with 0, I get 1, right? So if I XOR something with all zeros, I just get the thing back. So this is an identity element with respect to XOR operation, right? What is sort of funny is what is the inverse? Huh? The number itself. Yeah. So in this definition, you need to like look at it as like law or code. Nothing prevents you from having the inverse to be the same thing. So A can be its own inverse. That's what the case here. So if I XOR some number with itself, I get zeros, and if this is my identity element, I have perfectly valid group. So those are just very few examples. There's many more groups. And the cool thing is that next we will prove some basic properties of groups, and they will apply to all these groups. And probably the most important example, which we'll discuss in a little bit, are invertible matrices. They also form a group, and therefore proving general group properties will directly translate to properties of matrices, invertible matrices. The invertible, that's sort of like having to take out the 0, right? So that I have a defined inverse for every element of my group. All right, so let's take a look. What can we say in general about groups? So in general, they are not commutative groups, right? But there is, in the special case, that if A dot B gives me identity, then I actually can swap the order. This is the content of this theorem. So if E is the identity, therefore any A and B from the group that multiply together to E, then I can swap the order and I still get the identity back. So let's take a look how this is proven. So the proof, you probably had some proofs before, right? This works directly by applying the axioms of the group, the definition, the properties. I think axiom is the best word of the group, right? So let's see how this works. We need to like think about it a little bit carefully. So what we need to prove is that B dot A will be E, right? And we know that A dot B is the identity. So B dot A is going to be some element in the group, right? From the closure. It has to be. So every element has an inverse, right? So we can say that Y is that inverse, right? So then if this is the inverse, then it means that E is B dot A dot Y, right? Because Y is the inverse of this. And because E is identity, I can as well multiply the B with identity, right? That's the second step. I just stuck in the identity inside here. B dot E is B, right? So nothing has changed. It's equal. What happens next? Now I use the fact that A dot B is identity. So this E I can replace with A dot B, because this is what I assume. I assume that A dot B is identity. And here I use the associativity. That means that I can flip the order of brackets, the order in which I'm computing this multiplication, right? So here I was computing first A dot B and then dot B and then dot A, but I can also do it like doing B dot A and B dot A. As long as I don't flip anything, which I didn't, this is BA, BA, this is also BA, BA, this is also equal, right? And now remember, Y was the inverse of B dot A, right? So this is E, right? But anything times E is the same thing, so B dot A times E is just B dot A, which means that B dot A is E, and that's exactly what we wanted to prove. So that's sort of cool. That's like a logical sequence of applying these axioms. And we got that we can actually, if A dot B is identity, then B dot I is also identity. That's what we have proven here. So in particular, this implies that the inverse it doesn't matter if you multiply with the inverse from the right or from the left. Either way, we got the identity, right? Remember that in the axioms it was only defined from the right. I can bring it back if you don't remember. The axioms only required the E to multiply from the right, and the inverse also just worked from the right. But here we have shown it actually doesn't matter, that once we have it from the right, it also immediately is equal to multiplying from the inverse from the left. Okay? Here is another similar theorem. And that thing is true for any group. So this one says that a right identity is left identity. So it means it doesn't matter if I multiply with identity element from the right or from the left. So it's sort of in a similar way. We define the identity has to have this property that A dot E equals A, but we so far don't know what happens if we multiply from the other side, because it can be in general non-commutative. And here is a proof that actually from the very axioms of the group we can derive that this is also going to be A. So the left multiplication with the identity is the same as right multiplication with the identity. All right, so let's take a look how it works. So we know that E is the identity element, right? And we are trying to prove that if we multiply some arbitrary element A, so we pick some arbitrary A, and we are left multiplying it with identity. So identity I can write as A dot A minus 1, as A inverse, right? Because every element has an inverse, and the element times its inverse is identity. So here I just rewrote the identity this way. Next, we again apply associativity. Associativity is really beautiful property. So we can, that's actually where the trick is, right? That's why we get it from the left to the right, just due to associativity. You can see it here. Because then the A inverse times A is identity, and we know that right multiplication with identity gives us A back, right? So indeed, E times A is A. So the left multiplication with identity does the same thing as right multiplication with the identity. So that's summarized here. Okay, got it? So this is like elementary group theory. Here is another elementary result of group theory, the uniqueness of identity. So the point of doing things so abstract is that ultimately they will apply to matrices, but they will apply also to other objects of matrices, or specifically some certain special classes of matrices, like the orthonormal matrices, for example. So that's the point of doing things like so abstract, right? Like might be like weird, like doing things like in such an abstract way, but on the other hand, it's sort of cool that what you can just say in general. So the next property is the uniqueness of identity. So it's saying that if we have two identity elements, that they have to be the same. That there cannot be two identity elements, two distinct identity elements in a group. The identity is unique. And the proof is very simple. So assume there are two identity elements. There is E1 and E2, and both of them have the property of the identity element. That any element times E1 and any element times E2 is back A, right? So A times E1 is A, and A times E2 is also A. And using the previous theorem, of course, it doesn't matter. We could also hit it with each of them from the left, right? Because they are identities. So let's see, because because E1 is identity. How does this work exactly? Because E1 is identity, then I would have that E1 dot E2 equals E2. Right. Because E2 is also identity, then also this is true, that I can flip it. That's from the previous theorem. The same is also true for E2. So E2 times E1 also has to be E1. E2 times E1 also has to be E1. And because these things have to be the same, that it follows that E1 has to be the same as E2. So it's slightly confusing, but I think the idea is actually very simple. Let's try to look at that again. Exactly is the logic. Yeah, no, I think we really have to use the fact that if this is simply using the previous theorem, that it doesn't matter if we multiply it with the identity from the left or from the right, right? So this is just using that E1 is identity. So if E1 is identity, then we know that E1 dot A is the same as A dot E1, and it's A, right? And then for A, we just substitute E2, because this has to be true for any element, so in particular E2, right? Yeah, so that's how this. It's sometimes funny to recover the logic, but it's ultimately relatively simple. So the conclusion is that if there are two identity elements, they actually have to be the same. So there are no two different identities unique. Yep. Okay. So we had uniqueness of identity, and we also have a uniqueness of the inverse. So we know that there is an inverse for every element. That's what the axioms require, right? And we also know now that it doesn't matter if you multiply with the inverse from the left or from the right. But this theorem says more. This theorem says that there is exactly one inverse element. That I cannot have like a bunch of inverse elements, right? The axioms don't tell us that. It's up to us to actually deduce it from these axioms. And that's what this proof is trying to do. So again, we will assume that there are actually two inverse elements, right? So that both A1 and A2 are inverse of A, right? So it means A dot A1 is the same as A dot E2, and it's the identity. Now I can multiply this thing, this whole thing with A2, right? So I just multiply this with A2. Again, you probably can see what's coming is the associativity trick. So this is just A2 dot A times A1 is identity. So it's A2 times identity, which is just A2 because E was identity, right? Here comes the, so here I just use associativity. I flip the order of multiplication, and I see that A2 times A, the result times A1 is back A2. And here I use the fact that A2 times A, which is the same as A times A2, is identity. So this is just identity. And identity times A1, this is so confusing. Identity times A1 is just A1, of course. Because this is the same thing that this follows, that A1 has to be A2. I think the best way to like grasp these proofs is just to basically try to derive them yourself on a piece of paper. It's actually probably even better than just taking notes here, to just like try to do it. Just try to apply these axioms by yourself. I'm just trying to like narrate it here, but I think you won't really fully get it until you try to like write it by yourselves. Okay, and here we go. The whole point actually of talking about groups in this course are the matrix groups. The set of invertible n matrices. So invertible, it means the inverse exists, right? I was saying that not all matrices have an inverse, but here I'm just taking the ones that do have an inverse. And these matrices form a group under the operation of matrix multiplication. So matrix multiplication is my group operation. Notice that it is definitely not commutative, right? But it satisfies all the properties of a group. You will check it here. This group is called GL, which means general linear group. General linear group in n dimensions. So GL n is a subset of R times, this is like a subset symbol. But the GLN is a group, right? So these just n by n matrices would not be a group because I cannot invert singular matrices. So it's the same idea as with the real line, where I have to take out the 0 so that I can actually invert, because in a group every element has to have an inverse, right? So we need to check the axioms of a group. So the first one is, if we multiply two matrices together, I need to get back an invertible matrix. So if A and B are invertible, the product also needs to be invertible. And that's true, right? Because what we discussed before is that the inverse of AB is just B inverse times A inverse, and clearly if I multiply these together, I get the identity. So this is the inverse of AB. So the inverse exists, and therefore this set is closed under the operation of matrix multiplication. So associativity simply follows from matrix multiplication associativity. This is this property for matrix multiplication. That doesn't even need the inverse, right? That works for any matrices, any square matrices. So this by the way implies it's square. Now the identity element is obvious. That's our identity matrix, right? You know that if you multiply any matrix with the identity, you just get the identity back if you are talking about square matrices. So if I take a square matrix A and I hit it with square n by n identity, I just get A back. So this is my identity element. And inverse obviously is the matrix inverse, right? So that's what I was talking about last time. How do we, oh actually I have the slides to refresh that, how the inverse matrix is constructed. So from the point of view of the group, that will be my inverse element. I assume that the inverse exists because I only picked the invertible matrices, so I don't have to worry about the inverse not existing because I took care of it. So this is just to recap inverse, which we were discussing the last time. The inverse matrix is such that multiply with A, it gives me back identity. In general, doesn't have to exist. And this is how it's found. So just to refresh your memory, this is what we had the last time. So if I have some matrix like this, how do I find the inverse? Well, I can solve these three linear systems, and these columns x1, x2, and x3, they are the columns of my inverse matrix. So this is the solution. And this is the best part. This says that not only all the results from groups apply to invertible matrices, to the GL group, but the interesting thing happens, there are actually subgroups of GL, which are also groups. So subgroup means it's a subset, which is a group by itself, right? So I have some big group here, and I can pick some smaller set, which is completely contained in the bigger set, and the smaller set happens to be a group by itself. So the groups are sort of nested. The GL one is the biggest one, and there are some special smaller subgroups. So one of them is the group of matrices, the group of orthonormal matrices, the capital ON. Doesn't matter if it's orthonormal columns and rows, in both cases it's orthonormal. And that's because if I multiply orthonormal matrices together, I get again an orthonormal matrix. Now, the group of orthonormal matrices with determinant 1, this is group of rotations. This is called SON. This is for special orthonormal or special orthogonal. I think it's actually a special orthogonal group, but it's just terminology. I think it really means the orthonormal. And we also know when we are talking about LU that lower triangular matrices, when multiplied together, give me also a lower triangular matrix. So invertible lower triangular matrices form also a group. And so the same thing, of course, for upper triangle matrices. And permutation matrices is another special subgroup of orthonormal matrices. So there's like an entire zoo or hierarchy of groups within matrices. And the connection between groups and matrices is actually even more intimate, but that we're required to go a little deeper in group theory. Group theory is something you could be studying for like your entire life. So this is just the tip of the iceberg. So the important conclusions for us that are useful for matrices. So this is just applying the results I was showing here, all these theorems that apply for general groups. We can apply to GLN, to our general linear group, the invertible n by n matrices. So the first thing, so one of the things I proved is that it doesn't matter if I multiply with the identity from the right or from the left, right? So this immediately tells us that I can multiply the identity matrix from the right or from the left. It doesn't matter. This is sort of trivial to see directly, but it follows from the basic group theory. Now, something more interesting probably is that the identity matrix is in fact unique. There is no other matrix that, if I multiply it with arbitrary matrix, would just give me the matrix back. Only the identity is the only one. The other thing is that matrix inverses are unique. So you cannot have two different inverse matrices for one single matrix. Again, follows directly from the group properties. So we don't even have to know that they are matrices. So it's true for general groups. And one very practical thing is that the right inverse and left inverse is in fact the same thing. So it doesn't matter if I multiply with the inverse matrix from the right or from the left. In both cases, I just get back the identity. So it's unique, identity is unique, and I can flip the order in this special case that both matrices multiply to identity. So this is what we learned from group theory, and it applies to matrices, matrix multiplication, assuming the matrices are invertible. All right, so this was the group theory lecture. Do you have any questions? If not, then I'll just see you on Friday.